Page 7 of complex numbers and polynomials. Okay, number 7a. If z equals a plus bi, find z squared in the form x plus iy. So we have a plus bi times a plus bi. That's equal to a squared negative b squared. And the two inner terms are plus abi plus abi. So that's equal to a squared minus b squared plus 2abi. So x is equal to that, and y is equal to that. Hence, show that z squared conjugate equals z conjugate squared for all complex numbers z. Okay, so I'm going to take a squared minus b squared plus 2abi, and I'm going to take the conjugate of that. It's going to give me, the real part's going to stay the same, and then the imaginary part is going to become minus 2abi. And then I can compare that to a minus bi squared. That's going to be equal to a squared minus abi minus abi plus b squared. I'm sorry, minus b squared, because negative b times negative b is b squared. I squared is negative 1, so it'd be still negative b squared. So the real part would be a squared minus b squared. And the imaginary part would be minus 2abi. Imaginary parts equal, real parts equal. Okay, now it says to do a and b again, except for with z cubed. So let's use this space up here. So we already found z squared. Let's find z cubed. I'm going to multiply this times a plus bi again. So I got a squared minus b squared as the real part, plus 2abi as the imaginary part. I'm going to multiply that times a plus bi again. So that's going to give me a times a squared minus b squared plus 2a squared bi plus b a squared minus b squared I minus 2ab squared. And so the real part would be this and this would be the imaginary part. So the real part would be a cubed minus b squared a minus 2ab squared. And then the imaginary part would be 2a squared b plus, and there's another a squared b here, so it'd be 3a squared b, 3a squared b, and then b minus b cubed I. One more simplification. So these two are like terms. So a cubed minus 3ab squared plus 3a squared b minus b cubed I. Okay, so that is the result for z cubed. And then we want to change it to z cubed conjugate, right? So let's take the conjugate of this. The conjugate of this, the real part would be the same, a cubed minus 3ab squared, and then this part is going to be minus 3a squared b minus b cubed I. So that's z cubed conjugate. And then we want to, so that's z cubed conjugate. We want to find out now what z conjugate squared is going to be. So z conjugate squared, let's do that right here. So z conjugate squared would be this result. Let's recopy that here. A squared minus b squared minus 2abi. We're going to multiply this times z conjugate because we want to do z conjugate cubed. So z conjugate would be a minus bi here. Okay, so we'll have a times a squared minus b squared minus 2a squared bi. And then we're going to multiply everything times minus bi. So we'll have minus b a squared minus b squared I. And then we're going to multiply negative bi times minus 2abi. So we would get minus 2a, no, we get plus, yeah, I guess we get minus 2 ab squared, ab squared, okay? And, okay, now let's multiply everything out. So we have a cubed minus ab squared, and then we'll put the other real term, which would be here, minus 2ab squared, minus 2ab squared, and then put the imaginary terms, which would be minus 2a squared b minus a squared b plus b cubed I. Now let's simplify this a little bit. So these two are like terms, and these two are like terms. So we'll have a cubed minus 3ab squared minus 3a squared b. We can put plus negative minus 3a squared b plus b cubed I. Okay, so now we have this is equal to z conjugate cubed. And now we're going to compare this to this, which is z cubed conjugate. And yeah, the a cubed is matching. Minus 3ab squared matches. Negative 3a squared b matches. And plus b squared also matches. So it worked out. Okay, so we did repeat it, and we do have a match. All right, 9. Assuming that z1, z2 conjugate equals z1 conjugate times z2 conjugate, explain why this is equal to this. So let's take the left-hand side expression. So we have z1, z2, z3 multiplied times each other, conjugate. And we'll use this expression to kind of rewrite this expression. So let's group z2 and z3 together. And so that'll give us basically that this is z1 times the number z2, z3. And it's the conjugate of that, okay? And now we can kind of use this expression here. We have one complex number times another complex number conjugate. That is equal to z1 conjugate times z2, z3 conjugate. And if we have z2, z3 conjugate, then that is similar again to this, okay? And we could break down z2, z3 conjugate into z2 conjugate, z3 conjugate, and then we finally have the right side expression already in just like 4 steps or 3 steps. Okay? B. Hence show that, and now we have 4 complex numbers multiplied times each other. Okay, so now we know that like this is true. Okay, so now we just need to kind of repeat the same thing over again. So if we have z1, if we have this, let's start with the left side and we'll break that down into z1, one complex number, times a second complex number, which is the product of z2, z3, z4 conjugate. So that is equal to z1 conjugate times z2, z3, z4 conjugate. And now that we have z1, z2, z2, z3, z4 conjugate, that's the same thing as this expression here. So we could break that down into the conjugates of each individual one. So now we have z1 conjugate times z2 conjugate times z3 conjugate times z4 conjugate, and now we match the right side. So mission accomplished, right? Okay. Okay, so generalize your result from A and B. Okay, so it looks as if I have z1 to zn star conjugate. It's going to be equal to z1 star multiplied times all the z's in between 1 and n star. Given your generalization in C, what is the result of letting all zi values be equal to z? Okay, so if instead of different z values here, if they were all equal to z, that would be saying z to the n star equals z star to the n. Okay, that's it for page 7.